The first thing that often gets left out before you start solving problems like inclined planes is understanding the idea of the plane of acceleration. Now, we've never mentioned this before, but we have been solving all of our problems in the plane of acceleration. So let's take a simple example like a ball that's falling. As the ball falls down, it's accelerating in this plane. So we've been calling that the direction of acceleration. And there's only one plane and the acceleration is that direction, so we solve it in that direction. In the same way, if we have a block that's dragged to the right with a force, our plane of acceleration is also along here. So our acceleration acts like that. But what happens when that's not the case? What happens when we have a box that's dragged at an angle like this, but it slides along the table horizontally? In this case, our plane of acceleration is horizontal, parallel to the table. So this force isn't acting completely in the plane of acceleration. However, some of it is. So what we need to do in these problems is to figure out the vector component of this force. So if we call this Fp, only Fpx is acting in the plane of acceleration. So when we write our Fnet equation, we say Fnet equals ma equals, and we put our forces in, we would put in Fpx, not Fp. Why? Because the acceleration is only in the plane that Fpx is in. This gets a little bit tricky when we deal with blocks on an inclined plane. So in this case, the plane of acceleration is down here, parallel to the surface. So we only have two forces, if this is frictionless, acting on it. We have the force of gravity, the weight, and we have the force normal. So none of the force normal is in the plane of the acceleration. However, some of the force of gravity, the weight, is in the plane of acceleration. So the way this is done, I'll do it a little bit more formally in a minute when we solve a problem. But we end up making a rectangular box around that so that we can break up the forces into the plane of acceleration and the plane that doesn't accelerate. So in this case, this component of the force of gravity is in the plane of acceleration. So if we call this side Fg, the weight or force of gravity, then this component we could call Fg x. We could call this our x-plane. We've tilted our x-plane. Some teachers and textbooks use force parallel for the force that's parallel to the plane. You can use either one. And then this force right here, force, we could call this Fgy, is not in the plane of acceleration. So when we write our Fnet equation, we say Fnet equals ma equals, we're only going to put in the Fgx, not the Fg. And the last part of this that you need to know is that this angle theta is equal to the interior angle of this triangle right here. And there is a geometric proof that shows that. But the reason it's true is because this triangle is mathematically similar to this triangle. So let's go ahead and solve an actual problem. Let's say we have an inclined plane like this, and we'll say that this is a 30-degree angle, and we'll put a box on the inclined plane, and we'll say that the mass of that block is 2 kilograms, and we'll say that there's no friction. So let's find Fgx, Fgy, and we'll use the Fgx to solve for the acceleration. So to do this, we first need to draw our free body diagram. So we have Fg acting down, then we make our plane, the plane that's perpendicular to acceleration, and then our plane of acceleration. Now, we need to break up this force into FGX and FGY, and the way that we do that is to make a rectangle. And if you do this correctly, you should have a right angle there and a right angle there. So let's label this FG, that's our weight. And then we'll break this up into FGX and FGY. And then we can throw in our force normal, because we know that the force normal is going to be opposite FGY, and that's what's going to cancel it out and keep it from accelerating in the y plane. So we will start out by saying Fg is equal to mg. We have to find this weight component, and that's going to be equal to 2 kilograms times 9.8 meters per second squared. So our weight is going to be 19.6 newtons. So now we need to find FGX. Well, we know this angle in here is 30 degrees, and we have a right triangle. So this side, this component in a right triangle, is also equal to this side. So what do we have? We have opposite and hypotenuse. So we're going to do sine theta is equal to the opposite side, FGX, over the hypotenuse, which is FG. So we have sine 30 equals opposite, that's our FGX, which is, we're just going to leave because that's what we're solving for. And then we have our FG, which is 19.6 newtons. So we cross multiply, and that gives us an FGX of 9.8 newtons. So what we have found is the horizontal component, or the parallel component to the plane that's acting in the plane of acceleration. Let's go ahead and find the perpendicular component, or FGY. So that's going to be cos theta. Why is it cosine? We have the adjacent and our hypotenuse that we know. So we have FGY over, that was a G, over FG. And that's going to be cos 30 is equal to FGY over 19.6 newtons. We cross multiply, and that gives us an FGY of 17 newtons. So we found this, but this has to be equal to Fn. So when we found FGY, we also found the force normal. So the force normal is 17 newtons. But the last question was, what's the acceleration? Well, to find the acceleration, we're going to write a net force equation. So F net equals ma equals, and what forces are acting in this plane of acceleration? Only FGX, and we know FGX is 9.8 newtons. So we can throw our numbers in there, and we have F net equals 2 kilograms times A, and that's going to be equal to our FGX, which is 9.8 newtons, and our acceleration comes out to 4.9 meters per second squared. Here's a common question. We have a block at rest, and they want you to find the force of friction. So the first thing to realize is that the block is being pulled down the plane by FGX. So there's a component of force, of gravity, our Fg, that is pulling it down this way. But if there's friction and it's at rest, then there must be a frictional force acting up the plane. And if it's not moving, that means the acceleration is 0, so the net force is 0, so these forces cancel each other out. So in other words, when we're looking for the force of friction, really all we're looking for is FGX. So let's go ahead and find FGX. We have our rectangle, we've broken our FG up into FGY and FGX, and our FGX is this opposite side here, so we're going to use sine So sine theta equals opposite, which is our FGX, over FG. And we have sine of 40 is equal to FGX over force of gravity. So that's going to be mass times gravity. That's going to be mg, so 10 times 9.8. That's 98 newtons. And if you cross multiply, that ends up giving you 63 newtons. So the question was, what's the force of friction? Well, we know that the force of friction has to be equal to FGX, so that's the answer. The force of friction is 63 newtons. Now, getting into more complicated problems, this might be an honors problem or something that you start to get into in a college physics class, would be what happens if we applied a force up the hill that drags the block accelerating up the hill. So let's say there's a force of pull up the hill of 100 newtons. What is the acceleration? So now we're solving for the acceleration. We're going to say that there's no friction. So what are the forces that are acting in the plane of acceleration? Well, we have Fp, the force of pull up the plane, and then we're going to have Fgx. And you're going to see in a minute that Fp is larger than Fgx, so that means we have a net force up the plane and it will accelerate up the plane. So let's go ahead and write our Fnet equation. This is going to be Fnet equals ma equals, and I'm going to call up the plane to be positive because that's the direction of the acceleration. So up the plane is positive, so we have a positive 100 newtons. And then we're going to subtract the component, the Fgx. Well, we already found Fgx in the last problem, so that's 63 newtons. So what's the mass of the block? We have 10 kilograms times A equals 100 minus 63. And when you subtract these and divide through by 10, the acceleration comes out to 3.7 meters per second squared. It comes out positive, which tells us that the acceleration is up the plane. Now, another question that's more like an honors or maybe even an AP question would be to do this without numbers. And that would be doing it as a derivation. So, in other words, can we find acceleration in terms of the values that we have times mass and gravity and the angle? And also, what would be the force normal as a derivation, just in terms of quantities? So, in this case, we have just a block. The block is m, and the angle is theta. So again, we do what we've been doing here, which is to break up our forces. So here's our FGX and our FGY and our FG. And then we also have our force normal. And we're going to do this with no friction. So what is our FGX equal to? Well, it's equal to this opposite side. So we do sine theta equals opposite FGX over hypotenuse, which is FG. And we now know that this is equal to mg. We're not going to put numbers in this time. So we have sine theta equals FGX over mg. In other words, FGX, when we cross multiply, is mg sine theta. So now we can write our Fnet equation. Fnet equals ma equals mg sine theta. And we have mass on both sides, so we can cross that out. And we're left with A equals g sine theta. And that's our answer. That's a derivation. Now, how would we find the force normal? Well, the force normal would be doing this for the cosine. So we would have cosine theta is equal to, oops, I missed a y there, FGY, adjacent, which would be FGY over FG. Our FG is equal to mg, so we have cos theta equals FGY over mg. And therefore, we can say that FGY is equal to cross multiplying mg cos theta. And because FGY is equal to Fn, this is Fn. So Fn equals mg cos theta. So we've done inclined planes, but the other type of problem is a block that's being dragged by a rope or a cord at an angle. And this involves the same sort of concept because our plane of acceleration is horizontal, parallel to the surface, but our force is not. So we need to find the force that is parallel or horizontal. So we're going to find this component right here, and that's going to be our FPX. So to do that, we have the angle. This is a right angle, so we have a right triangle. So we have the adjacent side, and our hypotenuse here is 65 newtons. So we're going to do cos theta equals adjacent FPX over our hypotenuse. This is FP. So we have cos 30 is equal to adjacent, our FPX, over hypotenuse, which is 65 newtons. So our FPX comes out to 56.3 newtons. But the question was to find the acceleration. So we need an Fnet equation. So we have Fnet equals ma equals, and that's going to be equal to our FPX because that's the only force that's acting in the plane of acceleration. So our mass, we said, was 10 kilograms, is times A is equal to 56.3 newtons. So our acceleration comes out to 5.63 meters per second squared. Now, the second question says, if there is friction and it's being dragged at a constant velocity, find that friction. So if you look at this problem, if it was at a constant velocity, there's no acceleration. If there's no acceleration, there's no net force. So the net force has to be zero. Well, how could we have a net force of zero? Only if we had a force of friction that was equal to FPX. So what would the force of friction be? If it's dragged at a constant velocity, it would just be the same value as FPX, which would be 56.3 newtons. The hardest question, which is probably not going to be found on a introductory high school course, would be to find the force normal. Now, this gets tricky because we have three forces in the vertical plane. The one thing that's nice about this is that the acceleration is zero. So we have acting down right now, we have a force of gravity, and that's mg, muga, so that's 10 times 9.8, so that's 98 newtons. But we have two forces acting up. We have FPY, but we also have some normal force that's acting up. Now, we don't know yet whether that force normal is larger or smaller, but we'll just draw our vectors like this until we find out. So if you see what we need to do here, we have 98. We're going to look for this force normal, so we need to get FPY. So to do that, we're going to use opposite. That's our FPY over here. So that's going to be sine. So we're going to do sine theta equals opposite, which is FPY, over hypotenuse, which is going to be our force of pull. So we have sine of 30 is equal to Fpy over 65 newtons. So Fpy is equal to 32.5 newtons. But that's not the end of the story. We still need to figure out the force normal. So let's just sort of redraw this again. And I'm going to call up to be positive and down to be negative. So we have our force of gravity down, we have our Fpy up, and we have our unknown force normal, which is going to be also up. So now we write our net force equation. F net equals ma equals, and now we add them. So we have two positive values, plus Fn plus Fpy, and Fg is down, so we have minus Fg. And here's the nice part. It's not accelerating in this plane, it's only accelerating this way. So A is 0, so this drops out to 0. So we have 0 equals Fn plus our Fpy, which was 32.5 newtons, and our Fg, which was 98 newtons. And what we're going to do is subtract these two values. So we end up with Fn minus 65.5 newtons equals 0. And then we can add this 65 to the other side. So our force normal comes out to 65.5 newtons. Now, one last thing. Fn turned out to be larger than Fpy. So our diagram would actually look like this. Fpy would be shorter and Fn would be longer. But we don't know that when we first draw the diagram. We have to solve the problem to find out how big Fp is.